In this video, we present TruFaaS, a trust verification framework for FaaS. FaaS stands for Function as a Service. FaaS allows developers to run applications without the need to manage servers. FaaS is lightweight, easily manageable, and cost-effective. There are several proprietary FaaS platforms like AWS Lambda, as well as open source platforms like OpenFaaS and Fission, and TruFaaS is based on these open source FaaS platforms. Now let's look into trust in FaaS. Trust is a concept used in computing and has been addressed at various levels from hardware level upwards. In our context, trust in FaaS can be defined as the function invoker's ability to feel confident that the function they are using is the exact function deployed by the function provider in the first place. Now let's look into our motivation. Our motivation for this project is that with the increasing popularity of FaaS, more and more mission-critical applications have begun to adopt it. It is important for such mission-critical applications to have the ability to trust the functions they use. However, currently little work has been done to address the issue of trust in FaaS. Now let's look at the problem at hand. A lot of research has been conducted to find out how the functions on serverless platforms can be compromised. By the use of vertical attacks by malicious tenants, attackers can modify function code and attributes of functions of other tenants. This can cause the function to execute a malicious code that could potentially disrupt the entire application and lead to catastrophic outcomes. So, the lack of function verification creates trust issues. The problem that we are addressing is how to come up with a mechanism that can enable trust verification in FaaS platforms. So these are the objectives of our research, and we have three main objectives. Our first objective is to propose a framework architecture that a function invoker can use to verify trust of functions in a FaaS environment. Our second objective is to provide a quantifiable measure of trust that can be used to verify the trust of a function. And our final objective is to propose a protocol for trust-related communication. So now let's look at the TruFaaS architecture. The TruFaaS architecture consists of two main components, the internal component and the external component. First, we have the internal component. It resides within the FaaS platform. The main responsibility of this component is to extract the necessary function information from the FaaS platform and send it to the external component. Function information here refers to the source code and other attributes like function timeouts and resource allocations that are needed to run a function. The implementation of this component will depend on the underlying FaaS platform. The next component is the external component. It resides outside of the FaaS platform and is responsible for trust calculation, trust storage, and trust verification. For trust calculation, we use the SHA-256 hashing algorithm to hash the function information received from the internal component. For storing these trust values, we use a Merkle tree, and we store the root of the Merkle tree in the hardware TPM. The trust verification process uses the Merkle root stored in the TPM and the Merkle proof. In other words, we traverse up the Merkle tree during the trust verification process. So now let's go through the complete function deployment and invocation flows with TruFaaS. The function deployment request of the function provider is intercepted by the internal component. It extracts the necessary function information, which refers to the attributes and the hash of the source code, and sends that information over to the external component. The external component then hashes the received information, updates the Merkle tree structure, and updates the root hash stored in the hardware TPM. Now, when the function invocation is begun by the function invoker, again the internal component will intercept the request and extract the function information related to the function to be executed, and then send it over to the external component. This external component then hashes the information and cross-checks that trust value with the trust value stored in the Merkle tree. If those values don't match, trust verification fails and function invocation will not go through. The trust protocol is used to give an additional layer of confidence at the application level to the function invoker, ensuring that the trust verification result has not been altered since it was sent from the external component. So we assume that all these communications happen over HTTPS, and our trust protocol is built on top of HTTPS, and we use the message authentication tags and elliptic curve Diffie-Hellman key exchange. So first, the function invoker generates the key pair. Then the invoker public key is sent to the external component through the FaaS platform. Then the external component will then generate their own key pair and use the function invoker's public key and create a shared secret. Then it will generate the MAC tag using this shared secret and the trust verification result. Then this MAC is sent along with the trust verification result and the external component public key back to the function invoker. Then the invoker can use his private key and the external component's public key to generate the shared secret. Then the shared secret and the trust verification results can be used to verify the MAC. If MAC verification fails, someone has tampered with the trust verification result. So now moving on to implementation, we implemented TruFaaS on Fission, which is an open source serverless framework that runs on Kubernetes. We used Golang for development and modified the function deployment and invocation flows to accommodate TruFaaS. The internal component was implemented as a platform-specific package, and the external component was developed as a Golang REST API. So, as you can already guess, the potential downside of our approach is how much latency it will add to a function's execution time. So, in order to find that out, we created an experimental setup where we take the time taken to deploy and invoke the nth function, given that there's already n-1 functions on the platform. The reason we went for an approach like this is that the main cause of latency would be the storage and the traversal of the Merkle tree, and the latency would increase with the number of functions stored within the Merkle tree structure. So the left side graph shows the comparison between vanilla Fission and Fission with TruFaaS for function deployment times. The right side graph is the regression curve fitted for the data points, showing the percentage increase in function deployment time. As you can see, the overhead increases as the number of functions deployed increase. And this is mainly because as the number of functions deployed increases, the time taken for trust value insertion increases. The increase in overhead observed in the graph is below 4% in the range tested. And it is important to note that the overheads are in the order of a few milliseconds. These are the graphs for the function invocation times. Same as before, the left side graph shows the compared times for the two versions of Fission, and the right side graph shows the regression curve fitted for the percentage function invocation time increase. From the graphs, we can observe that the function invocation time overhead originally increases and then levels off at a constant value. The overhead is in the range of approximately 15% in the range tested, and this is mainly due to the time taken for Merkle tree traversal during the trust verification process. So now let's go through a demonstration of TruFaaS. So here there are two actions, the function creation or deployment and the function invocation. So let's start with the function deployment. So generally a function provider will use a command line interface for function deployment, but we have developed a user interface for demonstration purposes. Now I will deploy a function and I'll just name it demo function. So here I have a simple prime generator function, and now I will create the function. So on the right side, you will be able to see the function creation results. So as you can see, the function was created successfully and the trust value was also created successfully. Moving on to function invocation. So again, this will typically be done programmatically using code within an application. But here, this UI was created for demonstration purposes. So now if I try to invoke the function that I just created, and I will generate the private and the public key for the trust protocol. And now I invoke the function. On the right-hand side, you can see the function invocation results. This is the response body that will be sent from the function. And you can see that the trust verification is true. And this MAC can be verified using the trust verification result and the public key and this private key. So now I will perform a mock attack. So here what we do as a mock attack is we manipulate the function information stored within the FaaS platform. So if I perform the mock attack, so now you can see that the mock attack was completed. And now if I try to invoke the function, you will see that the function invocation was stopped since trust verification failed. and the trust verification result is false. And again, you can verify this MAC using this public key and this private key. This concludes our video for TruFaaS, a trust verification framework for FaaS. Special thanks goes to our supervisor, Dr. Sunimal Ratnayaka, for his continuing support and guidance. Thank you very much for listening.